Hello, I'm SA, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
In 1927, Paul Dirac irrevocably altered the landscape of quantum physics with his seminal paper, The Quantum Theory of the Emission and Absorption of Radiation. This work did far more than introduce incremental improvements. It resolved fundamental inconsistencies between classical electromagnetism and emerging quantum mechanics, paving the way for the genesis of quantum electrodynamics. The central issue stemmed from the prevailing treatment of the electromagnetic field as a classical entity, irreconcilable with Einstein's revolutionary concept of spontaneous emission, a phenomenon demanding a quantum explanation. Einstein's earlier work on the photoelectric effect and spontaneous emission, rooted in the concept of quantized energy packets, photons, presented a profound challenge to the classical wave theory of light. While quantum mechanics successfully described the discrete energy levels of atoms, it lacked a consistent framework for handling the interaction between matter and radiation. The existing semi-classical treatments, while offering partial explanations, treated the electromagnetic field as a classical background upon which quantum transitions occurred. This approach failed to account for the inherent quantum nature of light itself, specifically the particle-like behavior of photons. Dirac's genius lay in recognizing a necessity of quantizing the electromagnetic field, treating photons no longer as mere energy packets but as fundamental particles possessing definite energy and momentum, free subject to quantum mechanical. Dirac's approach represented a monumental shift in perspective. He boldly proposed a Hamiltonian formulation that incorporated interaction terms between radiation and matter, setting the stage for a fully quantum mechanical description of light-matter interactions. Prior to Dirac, the concept of treating fields themselves, and not only the particles, as quantum mechanical entities was in its infancy. The introduction of creation and annihilation operators, hinted at within his initial formulation, constituted an inventive mathematical framework for handling the emission and absorption of photons. These operators, acting on the quantum states of the electromagnetic field, allowed for the description of adding or removing a photon from a particular mode, thus providing a mechanism for quantum transitions between energy levels. Crucially, Dirac employed time-dependent perturbation theory, a technique refined over years of quantum mechanical study focused on atomic transition probabilities under external time-dependent sources. He calculated transition rates for both emission and absorption processes. The astonishing result revealed that these calculated rates precisely matched Einstein's phenomenological A and B coefficients, the coefficients of spontaneous emission, induced emission, and absorption, derived originally from purely thermodynamic arguments. This derivation from first principles provided compelling evidence for the validity of his quantized field theory. The A and B coefficients, previously empirical parameters, now emerged as direct consequences of quantum electrodynamic interactions. The influence of Niels Bohr's correspondence principle played a substantial role in guiding Dirac's work. This principle, which posits that quantum mechanical predictions should converge with classical predictions in the limit of large quantum numbers, offered a valuable heuristic for developing his quantum theory. Dirac meticulously ensured that his theory, while fundamentally quantum in nature, retained consistency with classical electromagnetism in appropriate regimes. He built upon existing semi-classical radiation theory, of them crucially transcended them. One important implication arising from Dirac's quantization was the concept of zero-point energy. Even in the absence of photons, the electromagnetic field possesses inherent ground state energy, a consequence of the uncertainty principle applied to the field oscillators. Although initially viewed with some skepticism, the idea of zero-point energy later found applications in explaining phenomena such as the Casimir effect, a direct consequence of quantum field fluctuations in vacuum. Dirac's paper did contain limitations. The calculations relied on perturbation theory, an approximation method valid only when the interaction between matter and radiation is weak. In situations involving strong fields or high-energy processes, perturbation theory becomes inadequate, necessitating more sophisticated techniques. Furthermore, the initial formulation encountered difficulties regarding infinite quantities arising from the interactions of charged particles with their own electromagnetic fields. These issues prompted the development of renormalization techniques within QED, procedures for systematically removing infinities to obtain finite, physically meaningful results. The theoretical framework presented by Dirac's paper laid the foundation for subsequent developments in quantum electrodynamics. Figures such as Richard Feynman, Julian Schwinger, and Sinitero Tomonaga extended and refined Dirac's work, culminating in a complete and consistent theory of light-matter interactions. QED not only explained all known electromagnetic phenomena with incredible accuracy, it also established a precedent for developing quantum field theories for other fundamental forces, the creation and annihilation operators, first introduced in Dirac's formulation, evolved into powerful tools widely employed in quantum field theory and condensed matter physics. They provide an efficient mathematical language for describing the behavior of many particle systems, from photons and electrons to phonons and magnons. The concept of second quantization, where fields themselves are quantized, has become a cornerstone of modern physics. The initial reception of Dirac's paper was enthusiastic, though challenges relating to its implications continued and evolved. The elegance and explanatory power of his theory quickly gained recognition within the physics community. The derivation of Einstein's coefficients from first principles was widely regarded as a triumph, solidifying the union of quantum mechanics and electromagnetism. While some physicists questioned the physical reality of zero-point energy, the overall impact of Dirac's work proved transformative. In summary, Dirac's The Quantum Theory of the Emission and Absorption of Radiation represents a landmark achievement in the history of physics. It provided a consistent quantum mechanical description of light-matter interactions, resolved inconsistencies between classical electromagnetism and quantum mechanics, introduced revolutionary concepts such as creation and annihilation operators, and laid the foundation for quantum electrodynamics. The paper stands as a testament to Dirac's profound insight and his enduring legacy as one of the giants of 20th century physics. In 1927, Paul Dirac delivered a profound synthesis of quantum mechanics and electromagnetism with his paper, The Quantum Theory of the Emission and Absorption of Radiation. This work stands out for its rigorous derivation of Einstein's and B coefficients from quantum mechanical principles and for formally introducing the concept of quantizing the electromagnetic field. This was not mere conjecture, it was a calculated move, transforming our understanding of light-matter interactions. Dirac addressed a fundamental inconsistency within the existing theoretical structure. Classical electromagnetism, which successfully described many phenomena, failed when applied to atomic systems. This resulted in paradoxical situations, such as the inability to explain the stability of atoms or the discrete nature of atomic spectra. Quantum mechanics, with its revolutionary concepts, offered a new perspective, though it had yet to be fully reconciled with electromagnetism. Dirac's work served to bridge this gap, establishing a consistent framework for treating radiation phenomena within a quantum mechanical His methodology involved treating the electromagnetic field as a collection of quantum harmonic oscillators. Each mode of the field, characterized by its frequency and polarization, was described by a harmonic oscillator Hamiltonian. This led to the introduction of creation and annihilation operators, innovative tools that elegantly described the processes of photon emission and absorption. The Hamiltonian for a single mode of the electromagnetic field can be expressed h½ times h bar times omega times a dagger plus a dagger, where h represents the Hamiltonian, h bar is the reduced Planck constant, omega is the angular frequency of the mode, a dagger is the creation operator of the annihilation operator. The creation operator, when applied to a state with n photons, creates a new state with n+1 photons. The annihilation operator performs the reverse operation, reducing the number of photons by 1. These operators obeyed specific commutation relations, reflecting the underlying quantum nature of the field. Using time-dependent perturbation theory, Dirac calculated the transition rates for emission and absorption processes. He treated the interaction between atoms and the quantized electromagnetic field as a perturbation to the atomic Hamiltonian. This allowed him to compute the probabilities of atomic transitions induced by the absorption of a photon or the spontaneous emission of a photon. The resulting rates corresponded exactly to Einstein's phenomenological and B coefficients, thus providing a theoretical justification for Einstein's earlier postulates. It was as if Dirac was not simply calculating or revealing a hidden harmony. To derive these coefficients, Dirac considered the interaction Hamiltonian, h' equals negative a times vard, where h' represents the interaction Hamiltonian, e is the electron charge, r is the position vector of the electron, and O is the vector potential of the electromagnetic field. The transition rate from an initial state I to a final state F is then proportional to the squared matrix element of the interaction Hamiltonian between these. Dirac's theory also addressed the issue of zero-point energy. The quantized electromagnetic field possesses a minimum energy, even in the absence of photons. This zero-point energy, though initially met with skepticism, has profound implications and is inextricably linked with the Heisenberg uncertainty principle. It suggests that the vacuum is not truly empty, but rather dynamic state teeming with virtual particles. Dirac's approach can be seen as a direct outgrowth of Heisenberg's matrix mechanics. Heisenberg's formulation of quantum mechanics emphasized the role of operators and commutation relations. Dirac adopted this operator approach, extending it to the electromagnetic field. Its influence is directly seen via canonical quantization, where the electromagnetic field's vector potential and its conjugate momentum are given operator status. Subsequent developments in quantum electrodynamics, or QED, validated Dirac's initial approach. QED, developed by physicists like Schwinger and Tomonaga, built upon Dirac's foundation. It extended the theory to include relativistic effects and successfully addressed issues such as renormalization, which were not fully resolved in Dirac's original formulation. While Dirac's initial theory contained limitations, its conceptual framework proved remarkably resilient, guiding all future developments in the field. The creation and annihilation operators, introduced by Dirac, evolved into cornerstones of quantum field theory and condensed matter physics. They offered a concise and powerful means to describe matter-body systems. In quantum field theory, they appear in the description of virtual particles, fields, and interactions. The impact of Dirac's work extended beyond theoretical physics. It paved the way for the development of numerous quantum technologies, most notably the laser. Lasers rely on the principle of stimulated emission, a phenomenon predicted by Einstein and elegantly explained by Dirac's quantum theory of radiation. Dirac's The Quantum Theory of the Emission and Absorption of Radiation laid the groundwork for future breakthroughs. It was a monumental step in our understanding of the universe. It demonstrated that the seemingly disparate realms of quantum mechanics and electromagnetism could be unified into a single, consistent theoretical frame. Dirac's 1927 paper, The Quantum Theory of the Emission and Absorption of Radiation, possesses significance beyond its immediate contributions to quantum electrodynamics. It fundamentally reshaped our understanding of the conceptual foundations of quantum mechanics itself, initiating crucial shifts in how physicists perceived the nature of light and matter and their interactions. Prior to Dirac's work, the quantum description of radiation remained incomplete, with light often treated as a classical electromagnetic wave, even as matter obeyed the newly formulated laws of quantum mechanics. Einstein's photon concept, which posited that light consisted of discrete quanta of energy, offered a crucial stepping stone. However, a consistent theoretical framework capable of describing the emission and absorption of these photons by atoms remained elusive. Dirac provided this, establishing the particle nature of light on a firmer theoretical ground. The central conceptual innovation of Dirac's paper resided in its application of quantum mechanical principles to the electromagnetic field itself. Rather than treating the field as a classical entity, Dirac subjected it to quantization, introducing the concept of quantum harmonic oscillators representing the modes of the electromagnetic field. This led to the revolutionary introduction of creation and annihilation operators, mathematical entities that respectively add or remove a quantum of energy known as a photon from a given mode of the field. This second quantization, as the procedure became known, held profound philosophical implications. It implied that particles, rather than being fundamental entities, could emerge as excitations of underlying quantum fields. This perspective represented a major departure from classical physics, where particles and fields were considered distinct and independent entities. Prior to this groundbreaking work, matter was seen as quantum, while light remained largely classical. Dirac's work elegantly bridged this divide, quantizing light and casting it in a new, particle-based frame. Consider, for instance, an atom in an excited state. According to Dirac's theory, the atom transitions to a lower energy state, emitting a photon into the electromagnetic field. This process is described by the annihilation operator acting on the initial state of the field, reducing the number of photons in the initial mode. Conversely, an atom in the ground state can absorb a photon, transition into a higher energy state. This corresponds to the creation operator acting on the field, increasing the number of photons in corresponding mode. The philosophical implications of this formalism extended beyond the unification of light and matter. The concept of virtual particles, transient excitations of the quantum field that exist for brief periods due to the uncertainty principle, emerged as a natural consequence of the theory. These virtual particles mediate interactions between charged particles, contributing to the observed electromagnetic force. However, Dirac's initial approach also possessed limitations. His theory, while remarkably successful in describing many phenomena, encountered difficulties when dealing with higher-order processes, such as the interaction of an electron with its own emitted radiation. These processes led to infinities in the calculations, a problem that plagued quantum electrodynamics for several decades. Subsequent developments, particularly the work of Richard Feynman, Julian Schwinger, and Shinichiro Tomonaga, provided a solution to these problems through the process of renormalization. Renormalization involved systematically removing the infinities from the calculations by redefining physical quantities, such as mass and charge. This procedure, although initially viewed with skepticism by some, ultimately proved to be remarkably successful, leading to predictions of unprecedented accuracy. Despite these later refinements, Dirac's original paper retains its seminal importance. It laid the conceptual foundation for quantum electrodynamics, providing the theoretical tools and the philosophical framework necessary for understanding the quantum nature of light and matter. Its influence extended far beyond theoretical physics, paving the way for the development of numerous quantum technologies. One tangible example is the development of the laser. Lasers rely on the principle of stimulated emission, a phenomenon that Einstein initially predicted but whose full theoretical explanation required Dirac's quantum theory of radiation. In a laser, a population of atoms is brought into an excited state. While a photon of the correct energy interacts with these excited atoms, it stimulates them to emit additional photons in phase with the original photon, resulting in a coherent beam of light. The creation and annihilation operators introduced by Dirac became cornerstones of quantum field theory and condensed matter physics. They offer a concise and powerful means to describe matter-body systems. In quantum field theory, they appear in the description of virtual particles, fields, and interactions. In condensed matter physics, they are used to describe the behavior of quasi-particles, such as photons and electrons. The influence of Dirac's work extends to modern quantum optics. Roy Glauber, building upon Dirac's quantization of the electromagnetic field, developed a coherent state representation of light, providing a powerful tool for analyzing the statistical properties of light beams. This work led to a deeper understanding of phenomena, such as photon antibunching and squeezing, which possess important applications in quantum communication and quantum computing. Another realm where Dirac's formalism demonstrates continued applicability lies within quantum computing. Quantum computing uses qubits, which are quantum bits that are the quantum analog of the classical Boolean bit. Using Dirac's formalism, quantum states are manipulated with precision and efficiency. In conclusion, Dirac's The Quantum Theory of the Emission and Absorption of Radiation represents a monumental achievement in the history of physics. It provided the first consistent quantum mechanical description of the electromagnetic field, laying the foundation for quantum electrodynamics and paving the way for a deeper understanding of the quantum nature of light and matter. Those subsequent developments refined and extended Dirac's initial approach. His paper remains a cornerstone of modern physics, its insights continuing to resonate in fields ranging from quantum optics to quantum computing. Its enduring legacy lies in its revolutionary shift in perspective, from treating light as a classical wave to recognizing it as a quantized field, forever changing our understanding of the fundamental constituents of the universe.
We really appreciate you tuning in to this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.